Sharing my screen. Right, so we are actually doing, we are basically trying to understand propagation of electromagnetic radiation through a plasma medium. Okay, so last time we did this dispersion measure, in which I gave you this, very quickly at the end, showed you this example of pulsar dispersion. So here I actually repeat what I mentioned. So here, pulsars are rotating neutron stars which emit very precise pulses at specific phases. So they are very good clocks because the time duration between these pulses is very precise. So for example, here there is a pulse at this time and then there's nothing. As the neutron stars emitting region sort of goes through our line of sight, we see this pulse. Okay, and what is shown here in this gray scale here is y-axis is the observed frequency and the x-axis is pulse phase. So the pulsar arrives earliest in time at highest frequencies. So you can see this high intensity. So this is basically pulse arrival at different frequencies. So if you are at high frequencies, the pulse arrives earliest, and if you are at low frequencies, the pulse arrives at later times. This is because of this dispersion that I mentioned in the last class, that the group velocity of electromagnetic waves is affected because of the plasma medium, right? We have this 1 minus omega p squared by omega squared term in the dielectric constant, right? And that gives rise to something called this dispersion measure, which is nothing but the integral of electron number density along the line of sight. So the phase speed, the difference in phase speed between different frequencies is proportional to or group speed. I mean, the group velocity is what determines the pulse propagation time. So the dispersion measure is proportional to the line of sight integral of electron number density, right? So so this is t. This is the time difference, or basically the time of let's see what this is. Just a second. Right. So basically, the last time what we had was I actually don't know what this time in second here in this formula is. I got this formula from somewhere. This cannot be the propagation time, because propagation time depends on the distance of the object. Perhaps this is the, okay, I think this is perhaps this so time delay relative to vacuum. I think time delay relative to vacuum propagation, right? So this is time delay relative to the vacuum propagation measured in seconds. Right. So this is that difference. Oops. This is that difference that arises because of this omega p squared term. And this omega p squared, if you recall, is proportional to the number density along the line of sight. So this dispersion measure is conveniently measured. So, you know, the CGS unit of dm will be number density times length, which is per centimeter squared. But it's more convenient to use parsec per centimeter cube because the length in the galaxy are measured in parsecs and number density is measured in centimeter cube. So that's a natural unit. So this is about this illustrates this pulsar dispersion in real data, right? So so how do we get? So for example, if you want to calculate the dm for this pulsar, how would one do it? Can someone speak up and tell me? So this is the given data. So you know the frequency and the pulse arrival time. Can someone tell me how we can measure the dispersion measure of this pulsar? You know, this pulse which travels through the ionized medium along the line of sight affects how fast or how slowly this signal decays on this graph. Can someone tell me like how we can measure dm in principle if you're given this? I have to take names. Let's see, Bhuvana. Can you tell me, like, if you're given the observed frequency and the time of arrival of the pulse, how can we measure the dm? And we know the frequency, right?
By measuring the delay.
Right. So you know, if you're given this graph, how would you like use this graph?
Okay.
Right.
By taking the difference like between two different frequencies.
Right. So basically, you know, if you have these two times, you know, basically this is T1 minus T2 is given by, so if T1 and T2 are the arrival times, so T1 minus T2 is this factor times nu1 to the minus 2 minus nu2 to the minus 2, right? So you can actually fit this nicely, and a useful way of doing it is where did it go? Right, so this, right, so this is dTp by d frequency, right? This is the slope. This formula that I derived last time in class. This is the slope of arrival time. So and the frequency. So the local slope gives you the dispersion measure. So for example, here, x-axis is like TP, you know, phase is like time, you know, arrival time, and the y-axis is like frequency. So we obtain d omega or d nu by dt, right? So the local slope of this thing, and we know the frequency, right? So you can see actually delta nu is much smaller than nu, right? 320, 340, 360, 380 is, you know, delta nu is much smaller than nu. So you can actually just measure the local slope here and just plug in this formula. You will get d. Do you get it?
Yes, sir.
We know the frequency, we know dt arrival time, we know the slope, we can measure the local slope, and we get this easily. So we don't have to use this nonlinear expression 1 by nu1 squared minus 1 by nu2 squared. We can linearize it because delta nu is smaller than nu, and that's what is done here. Okay. Okay. Now this can actually be very, very useful tool, this dispersion measure, because we have pulsars all over our galaxy, and in nearby galaxies we have discovered pulsars. So Let me actually show this graph. So this graph shows this dispersion measure, which is nothing but integral of electron number density dl along the line of sight, along various directions. Okay, so this is x-axis is the galactic latitude b. So here is just to orient you what I mean. So b means, right, b equal to 0 means that you're looking in the galactic plane, and b equals 90 degree means that you're, or plus 90 degree means you're looking towards the north of the galactic plane. B equals minus 90 degree means that you're looking towards the south of the galactic plane, right? Since most of the electron density is along the interstellar medium disk, right, we expect the dm to be highest for b equal to 0, right? So here these blue dots, blue circles show the dm as a function of galactic latitude b, and indeed you see that for the pulsars which are in the galactic plane, the dm is quite high, and as you go to b equals 90 plus minus 90 degrees, the dm becomes smaller, right? Okay. What do you expect? So if you can actually so now right, so can someone explain to me why this has a, how do we obtain this? This looks like almost like a mathematical curve, right? This data is sort of distributed as if it's almost like a mathematical function. Can someone explain to me how we can actually get this? So recall, right? All we are doing here is n times the length along the line of sight. So let me see.
So is it due to relativistic beaming?
No, not at all. Not at all. This is not at all due to relativistic beaming. Let me give you a hint. Okay, let me give you a hint. So basically take the interstellar medium like this. So this is the interstellar medium, okay? It is like a disk, right? And if you're looking towards, so if you're looking, if you're looking in some direction B, this angle is B, right? This angle is B, right? So if the number density is constant, so Ne is constant in this blue zone, and you're sitting here and looking at different regions. So what do you get? Number density times this length, right? What is this length? This length in the interstellar medium is nothing but height h by 2. Right, so let me actually annotate on this. So dispersion measure has a lot of practical application. It's very simple physics, linear physics, but very, very practical tool. Okay, so right, so let's see. So you have this, say this is the Milky Way disk, and you're located here, and you're looking at an angle B, right? Now I'm actually giving hint, and someone must speak up and tell me. So this is your height h by 2, and you're looking from here. What is your Ne times length? So Ne, let's assume there is constant electron number density in the ISM. So this is dispersion measure is proportional to Ne times length. So this is basic. So what is length? This length is h by 2 divided by cos B, right? So dispersion measure is proportional to Ne times h by 2 cos B. So can someone tell me what this mathematical function is as a function of B? Right. So this envelope, would correspond to pulsars which are at the edge of the ISM or beyond the ISM, right? So, you know, some pulsars can be here, right? Here, they will be inside the envelope, but the ones which are on the edge or outside will, you know, however far you put them, they will only have this much dm. So it forms an upper envelope here. Do you see that? This is nothing but 1 by cos b. And y-axis is log here, so you cannot see it nicely. This is just 1 by cos.
Sir,
Yes.
sir, what are those dots means? Those in the red ones?
Let's not go to red first. First talk about blue. Blue dots are pulsars, most of the pulsars in our Milky Way. Okay. So if you have an object in the Milky Way, its dm will be less than this, right? NEH by 2 cos b. So this envelope is nothing but 1 by cos b, right? When b is 90 degrees, sorry, when b is just a second. So dispersion measure cos 90. Am I messing it up? Just a sec. No, sorry, sine b. My bad. Actually, I did the wrong. This is sine. My mistake. Please correct me. Right, this is sine b. Right, this is h by 2 is equal to sine. Yeah, so this is not cos b. This is sine b. Otherwise, it doesn't make sense. Right, so this length h by 2 divided by this length is equal to sine b. So 1 by sine b. This is nothing but 1 by sine b. So when b is equal to 0, it sort of blows up. You can actually see that it just is like a singularity. When b equals pi by 2, you know, it reaches some constant value. Okay. And in fact, you should try to make a plot. Let me show you. Oops. Oh. You see, this is how it looks like.
Sir, here most of the means the dm is at b is equal to 0 is quite high. Means, sir, is there any means physical
Yes.
significance? Means there is physical significance, but at b they are quite high.
Yeah. So this is how it looks like. Do you see similarity between the plots? This guy and this guy. This will fit this upper envelope quite well. Now you were asking why is dm very high at theta equals 0. It's obvious, right? Because when you're looking through the Milky Way disk, you are looking through the whole plane, right? It should not blow up. It will only sort of saturate at, you know, it will saturate at the value where you will have this. If this is the radius of the ISM, so it would saturate at NE times radius. But radius is like 1,000 times higher than height. So how high is, so let me see. So the radius of the Milky Way is 10 kpc, height is like 100 kpc, so 100 parsec, so it's a factor of 100, right? Do you understand why if your theta of your b is 0, you are basically, you know, traversing much longer path than this path, right? So that's why for b equal to 0, this seems to blow up. It cannot blow up because it saturates at NE times R. Do you get it? Hello.
No, sir. So can you repeat it again? Means,
see, when you're looking in the mid plane of the ISM, the path length is very long, right? That's
yes.
why dm, which is NE times the path length, can be very, very high when b is close to 0. Basically, you're looking at this whole path length. But when you're looking perpendicular, you're looking at only small path length. right? That's the reason it has this shape. Anyway, you guys think about it. It's actually very, very simple. Right. So in this, someone was asking what are the other plots. So let's see. These are galactic pulsars, the blue ones. These, light blue ones are pulsars in supernova remnants. So supernova remnants are young pulsars, host young pulsars, because supernova remnants means that the massive stars died very recently. Okay, so you may know or may not know that young stars form in much thinner disk compared to rest of the stellar distribution. So that's why they are much closer to in the vertical direction. So that's why their DMs are small. These are large Magellanic Cloud pulsars. So they have to be above the pulsar dispersion measure for Milky Way. Because they have additional path length in LMC itself, right? So if you have a Milky Way line of sight, so suppose this is an LMC here, okay? So it not only has this path, it also has path length within the Large Magellanic Cloud. So this adds to the DM. So these are SMC. SMC is the Small Magellanic Clouds. It is about at the same distance, so you have the same. So now these red guys are something called fast radio bursts. These are very recent discovery, like less than 20 years old discovery of new, very transient pulsing phenomena, and their DMs are very, very high. So these FRBs are supposed to be cosmological objects that is very, very far from us, and they accumulate DM as their light passes through the ionized intergalactic medium. So their DM is much larger than the DM of the galaxy. So in fact, this argument was used to say that these FRBs, fast radio bursts, are cosmological. They don't come from within Milky Way, but from far away. So you see, such a simple physics tool is so profound. It tells us about so many different aspects. Now, while we are at it, this is again data. This is dm sine b as a function of z, the height from the galactic disk. And what it shows, so again, dm sine b, right? If you recall the formula that I wrote down, dm was proportional to, dm was ne l h by 2 sine b. So dm sine b should go like h by 2 at the edge, right? But if the pulsars are nearby, it will just be linearly proportional. The dm will be linearly proportional to the distance. Once they cross the edge of the ISM, it should flatten, right? Because there is no dm contributed when the light passes through the vacuum. So these dashed lines are the two models in which the h is 500 parsec or 800 parsec. You see the observed dm actually flattens like this. And this is the linear extrapolation. If the ISM keeps on continuing forever, this is how DM will go with the height in the ISM. So you see, measurements of pulsar dispersion measures actually tells us a lot about the distribution of electrons in the Milky Way and in the universe in general. For example, in the FRBs. FRBs are now being used to put constraints on the electron number density in the IgM and in the diffuse phases of the galaxies. Okay, so this is about pulsar dispersion. There is another phenomenon which I'm actually not going to talk about. So here you see this is a pulse at 2.31 gigahertz, 2.21, and going up to 1.41 gigahertz, and it has been de-dispersed, right? That is, this delay has been removed, and now it is sort of lying in. They are put on top of each other at the same phase. Does someone notice any difference between the pulse at high frequency and the pulse at low frequency, even after it has been de-dispersed? You see, this is the dispersion delay. This dashed vertical line shows the dispersion delay. But do you see any other difference between this and this, for example? Someone? What's the difference between this pulse and this pulse? Of course, the amplitude is small, but what else? Notice
There's a broadening.
the width of the pulse is larger at low frequencies, right? And this is because of pulse broadening. This is because of electron density fluctuations. So if there are density fluctuations in the medium, there is density. So density fluctuations means refractive index fluctuations. Plasma dense, Ne fluctuations, right? There are fluctuations of Ne in this line of sight. So that fluctuation makes the dispersion delay even at the same frequency, broaden. So this is called pulse broadening due to electron density fluctuations. So by measuring, by modeling these fluctuations, one can get a sense of what the density fluctuations in a medium is. So this is also used. So this is called pulsar scintillation. So these are called radio scintillation studies that are done in different. This is also one of the things that's popular in using pulsars as a probe of density of the ISM. So this dispersion measure or delay just gives you a sense of NEDL. This broadening gives you a sense of delta N squared. How much does density fluctuate along the line of sight? So it sort of puts constraints on the density fluctuations, which are supposed to be coming from turbulence in the medium. So it's very useful too. Okay, so this is it. So now I'll go to today's class. Any question? Okay, so we talked about dispersion in a plasma, dispersion of electromagnetic waves in a plasma medium. Now we will talk about something called Faraday rotation. So what is Faraday rotation? So let me first tell you the phenomenon. So this is rotation of the plane of polarization of a linearly polarized light as it travels through a magnetized plasma. So have any one of you done experiments on Faraday rotation of light? They shine microwave light and they have a polarizer, and then you have an analyzer after it propagates through the magnetized medium. Has any one of you done that experiment? Yes, no. Yes?
Yes, sir.
Do you guys remember it?
Yes, sir.
So there was something like this. So you have a plasma, plasma tube, and you put these Helmholtz coils, and you create uniform magnetic fields in this plasma column. And then you have an electromagnetic wave, linearly polarized electron. So you put a polarizer so that it becomes linearly polarized. And what you see is that the plane of polarization has changed. So the polarization angle is rotated. So who said that they have done it?
Sir, we did it in a different way. I think we vary the magnetic field due to which the plane changes.
Yes.
Means there was no plasma. I remember that, but due to the magnetic field, it changes the the plane. I remember.
What did you guys do?
I can't remember it properly, but it was.
So were you using microwaves for light? This light.
Yes, I so yes, sir. There were yes, sir. We were using it, but I can't remember it quite clearly because it was way back.
You were focusing more on writing lab reports than on understanding the phenomenon, huh?
Yeah. Yes. Yeah.
That's the tragedy of experiment.
I'll have a look on it again. Yeah.
See, this is a beautiful physics which has such great applications. So, uh, right. So, if you have magnetic fields along the line of sight, along the propagation of uh, light, what happens is that if it was so, if it was polarized like this before scattering, before going through this medium, after going through this medium, it will be polarized like this. So there is this angle introduced in the sense of polarization. And this angle is related to this magnetic field strength and the number density of this plasma. And basically NE and B parallel is what matters for this. Okay. Anyone else has done this experiment? No. Okay, let's talk about the physics of it. So this is the phenomenon that if you have linearly polarized light, as it passes through a magnetized medium, its plane of polarization is rotated. And what matters is the magnetic field along the line of sight. Okay, so let's do the mathematics now. Okay. So yeah, we know this. So we are again assuming non-relativistic electrons. V is much less than C, and we are assuming cold electrons. So that we don't take into account the plasma temperature, electron temperature, and we are assuming immobile ions or protons, because they have large mass, so they don't move as much as electrons do. Right, and we already know omega B is equal to EB by MC. Here gamma is equal to 1, so it's EB by MC because V is much less than C. This is about 2 times 10 to the 7 B per second if B is in Gauss, which is the CGS unit of magnetic fields. Okay, and this B, so we have this B naught. So we have this B naught, which is much bigger than delta E, and of course, which is bigger than delta E and delta B of the electromagnetic wave. So these electromagnetic waves have delta E and delta B. This B naught is the DC magnetic field due to this Helmholtz coil or whatever the magnetized medium is. Okay, so what is the electron equation of motion? M dV dt equals minus EE, because it's an electron negatively charged, minus E by C V cross V naught, right? This is the electron equation of motion. We did the problem, right? We did the Larmor motion and we ignored this because this was, this is basically due to electromagnetic wave, right? This electric field is due to electromagnetic wave. Previously, we did this problem where we don't have this term and we show that particles gyrate around magnetic fields in circular helical orbits. Now we have this additional complication, this electric field, which is passing, basically this fluctuating electric field due to this electromagnetic wave passing through this medium. Okay. Okay, so we have to solve this. Right, we know, so we are actually ignoring the V cross B by C term because V by C, we are setting this to 0 as V is much less than C. So we just have this. We made this assumption even in the previous case when we were doing DM. Okay, let's see. So we can actually take, let's take our coordinate system. So this is epsilon 3 hat, epsilon 1 hat, epsilon 2 hat. So x, y, z, basically epsilon 1 hat is like x, 2 is z, y, and 3 is z. So magnetic field is along the z direction. So what is V cross B naught? This is equal to minus V1 epsilon 2 hat plus V2 epsilon 1 hat times B naught. So this is just V cross B. So V can be written as V1 epsilon 1 hat plus V2 epsilon 2 hat plus V3 epsilon 3 hat. And you know, epsilon 3 hat cross B naught gives you 0 because B naught is equal to B naught epsilon 3 hat. So you get just this just by crossing the two. Good. And we assume, so assume velocity goes like e to the minus I omega t. The time variation of the velocity is e to the minus I omega t because it's excited by this wave, which varies at the frequency omega. So this is sort of like a driven oscillator at frequency omega of the driving force, which is electric field, which varies at omega. So what is d dt of V is dV dt is nothing but minus I omega V. So minus I omega V plus E B naught by MC V2 epsilon 1 hat minus V1 epsilon 2 hat. I'm just writing this equation of motion is equal to minus EE by M and now E is in the transverse direction. So you know, let me just write it as E1 epsilon 1 hat plus E2 epsilon 2 hat. Right, because you know it's a transverse wave. It can only be polarized in perpendicular to the direction of K, which is along, you know, B and K are along each other. Okay, so and all, you know, this electric field is also varying at frequency omega. Okay. So what happens is these are basically, you know, these are two equations for Vx or V1 and V2, right? But it turns out that things can actually simplify, right? So you know, let's see. Things can actually simplify because, you know, there is like this inherent circular motion here. So let me just do a little bit of a trick. So we can actually assume, so two equations for V1 and V2, and what we can actually do is we can assume a basis function. So we can choose R and L circularly polarized basis. So what are R and L circularly polarized bases? So basically this one, epsilon, so epsilon R hat is equal to epsilon 1 hat minus iota epsilon 2 hat and epsilon L hat right. So basically, what does this represent, right? This represents a right circularly polarized wave, and this is a left circularly polarized This is one wave. And the utility of this will actually be clear. So your electric field actually, so electric field can actually be written as, so what happens is actually the following. So this velocity is equal to minus iota E by m times omega plus minus omega b times electric field, right? So what happens is that the R and L polarizations decouple. So what I'm doing here essentially is, so I have a matrix equation, right? It's sort of like mv is equal to some right hand side. So this is a 2 by 2 matrix. So what I'm doing is when you have such an equation, right, you can actually write this in this form. When you have such an equation, and this, we can actually remove these vector signs. No, they are actually vectors. So there are, so right, because so we have equation for V1 and V2. Some matrix is equal to E1 and E2. This is the form of these equations. Actually, these vector signs go away. Right, so if you write it in this matrix form, so what when you have a matrix equation, what you normally do is diagonalize it, right? You get the eigenvalues and eigenvectors. So basically, this is the eigen decomposition of this matrix. So what you have is, if you write an electric field in this RCP and LCP basis, then your velocity also decouples in the right and left polarizations. Because it's sort of easy to see, because see, when you don't have this term, when you don't have the electromagnetic waves, we know that the particles go around in circular paths, right? So the wave will be affected. So the wave which has the same sense of polarization, circular polarization, as the rotation of the particles will behave differently from the wave which has opposite sense of circular polarization than the rotation of the particles. And that is what is reflected here, right? There is omega plus minus omega b. So when omega minus omega b, you can actually have cancellation, in this denominator. So right, so this is actually an important equation. So sorry, I'm not writing out all the steps here, but it is fairly easy and also physically plausible, right? Because what I'm saying is that this, in absence of this driving, you have circular motion, and when you have driving, the wave which is circularly polarized in one sense will behave differently from the wave which is circularly polarized in the other sense. Okay. So right, so for example, this basis function, what is the physical field for this basis function? So you have x and y. So so you will have cos phi. So you have, right, so you have e to the I phi as the phase. So the real part of that. So and you have minus I e to the I phi. The real part of this would be minus I times minus I plus I sine phi, which is equal to minus sine phi. right? So you have cos phi epsilon 1 hat minus epsilon 2 hat sine phi, right? So basically you have, this is one sense of, so this is one, this is how epsilon r hat, I think it goes in this direction, right? This is how this vector will go in time, right? The other one will be epsilon 1 hat cos phi. There is a plus there, so plus epsilon 2 hat cos phi. And remember, phi is equal to minus I omega t. So this is L polarization, this is R polarization, and the two behave, the two velocities in the R and L sense are given by these. So VR is equal to minus IE by M omega plus omega B ER, and VL is equal to the same thing, minus sign and EL, right? So it's actually obvious, it's pretty physically plausible that the basis function are these circularly polarized unit vectors rather than the linearly polarized unit vectors because of the circular motion of the particles. Okay, so any question on this?
No, sir.
Right. So the idea is that if you have linearly polarized wave, right, a linearly polarized wave can actually be written as the sum of, so this is a linearly polarized wave, a sum of R polarized, so this is an R polarized wave and an L polarized wave. This is right. So this is like the unit vector. This is unit vector on an R basis, and this is unit vector in the L basis, and this rotates in time like this, right? And this rotates in time like this. So when you add this and this, you get, of course, polarization in this direction. And even when you add this and this, you get polarization in this direction. So at all times, these R and L add up to give this linearly polarized light. So in other words, epsilon 1 hat is equal to epsilon R hat plus epsilon L hat by 2, right? If I add this and this, I get this. So this is just a diagrammatical representation of the fact that a linearly polarized wave can actually be written as a combination of circularly polarized waves. So what the idea is that this linearly polarized wave that we launch here on the left, this is linearly polarized, but it can be written as a sum of linearly, R and L waves, right? And the R wave and the L waves have different phase velocities as they move through this magnetized medium. And because of that, there is a phase difference added after they cross this medium. Okay, and that is what causes this plane of polarization to rotate. So let's see. Actually, let's continue. So this is the relation between V and E. Right, so N, E, V, J current density is equal to minus NeV, right? E here is the magnitude of charge of electrons, but the sign is negative, so I put an explicit negative sign. J equals NeV, so this and this is equal to sigma E. This is the definition of conductivity. J equals sigma E. Now if we compare this and this, compare this and this, basically, not this. So what do we have? You have sigma is equal to I n e squared by m omega plus minus omega b. See, the R and L polarizations have different conductivity, right? Because this is different. So so I'm just sort of comparing this ne squared minus minus sign, right? So we have that. So this is sigma, right? So you recall in the last class we did we wrote our equation del dot E. So right, del dot E is equal to 4 pi rho, where rho is the charge density. And what we did was we wrote rho, right? So we know that minus I omega rho plus I k dot j is equal to 0. This is the conservation of charge. So so this is I k dot E is equal to 4 pi rho is just k dot j by omega, and j is nothing but sigma E. So what do we get? We get I k dot epsilon E is equal to 0. Now this takes care of the polarization of the plasma, right? This is the dielectric constant, or it's actually a tensor in this case too, because the two polarizations have different value of epsilon. So so what do we get? So we get epsilon just by comparing, like writing epsilon in terms of sigma, right? We get epsilon is equal to 1 minus 4 pi sigma by iota omega, right? I mean, I'm just sort of comparing this and this time so this is I k dot 1 minus 4 pi k dot sigma, sorry, no, k, sorry, this k, what am I doing? K dot is outside, there is no, k dot is outside. 1 by 4 pi omega, and there is an iota here, right? So that's what I've written there. So your epsilon is that, and this is equal to 1 minus omega p squared by omega times omega plus minus omega b. This is the dielectric tensor for a magnetized plasma. This is how the R and L circularly polarized waves respond in a magnetized plasma. So you recall, it reduces to the previous case. If we put B equal to 0, it becomes 1 minus omega p squared by omega squared, which reduces to the dispersion measure case that we were dealing with when we considered B is equal to 0. So yeah. And recall, we have refractive index is equal to square root of n, square root of epsilon. Right, so this is so refractive index is nothing but V phase in a medium divided by C. So you see again, epsilon looks like it can be less than 1. So the phase velocity in a magnetized medium for electromagnetic waves is greater than C, sorry, this is C by VPH, not this right hand side is right. The speed in vacuum divided by speed in a medium is the refractive index. So you see, if epsilon is less than 1, you can have VPH greater than C, and that's what happens in the magnetized plasma, or even a plasma we considered previously. Okay. So now what happens? So what does it mean? So what it means is that right. So your K, right. So the wave number, right? So omega is fixed. K is equal to omega by C epsilon r comma L. Right. So the K, the wave number for the R polarized wave and for the L polarized wave are different because the epsilons are different. Right. They are given by this. So what happens is the two circularly polarized components, gather phase difference as they propagate along B. Right. So what is the phase? So phase is phi is equal to K dot D, where D is the distance. Right. So the two, so this wave, R wave, and the L wave will gather a phase difference delta phi is equal to Kr minus Kl times times the distance. So what is Kr and Kl? Let's see. Right. So from this equation, so Kr comma L is approximately omega by C, and then we have 1 minus omega p squared by omega times omega plus minus omega b, this whole to the power of 1/2. So we assume that omega is greater than omega p and omega is greater than omega b, and this is this is valid in most cases, because omega p is like 10,000. The frequencies that we are talking about is always greater than tens of hundreds of megahertz. So what do? We do the binomial expansion. So this becomes omega by C 1 minus omega p squared by omega squared. So this draws a half. And then we also do this again, the inside, 1 minus plus omega b by omega. Right? So we have just done a binomial expansion. So you see, this is just the dispersion measure, right? This is omega p squared by omega squared is just the dispersion measure. So Kr minus Kl is equal to what? It's omega by C. So the dispersion measure is equal in the two polarizations. So this term will cancel. So this is equal to omega by C omega p squared omega b by omega cube. Right, and your phase difference is, this is equal to basically k delta k dot ds. So this has to be integrated over the whole line of sight. So this is equal to, so delta k is nothing but kr minus kl, so that's omega p. Right. So let me just put down, so this is nothing but omega p squared by omega b divided by omega squared c. So this is equal to 1 by omega squared c. So integral of 4 pi e squared by me 4 pi n e squared by me, that's omega p squared, and omega b is e b naught, e b by mc. So b is here times dl. So your phase difference is equal to 4. So there is a factor of 2 there. No, this is fine. So this is your phase difference, right? So NE can vary along the line of sight, and so can magnetic field. And the important thing to notice is that this is B parallel. This is component along the line of sight, and in fact it can have positive or negative sign. And in fact, if you have paths where magnetic fields are changing direction, there can be cancellations. So one has to be careful. Right, so this is the phase difference. The phase difference introduced between the L and R circularly polarized components of a linearly polarized light is given by this. It's proportional to the number density times the B parallel integrated along the line of sight. Okay, so if you have a phase difference of delta phi, so let's see. So you have these. So this is the linearly polarized light initially, and as I said, we can actually write it as a combination of an R circularly polarized wave and an L circularly polarized wave. Now, as these waves are traveling through the medium, there is a relative phase difference introduced between these two. So what will happen is, instead of them aligning here at t equal to 0, right, we will have an extra phase for this wave. So how would it look like? So this is without phase difference. So with phase difference, what will happen is we can actually consider the this wave to be the same, but the other one will have a phase difference with respect to this at, say, t equal to 0. So this is at t equal to 0. This one will have some phase difference relative to this, right? And this is just delta phi, right? So if at t equal to 0 they are aligned like this rather than perfectly in phase, what happens if you add this and this? What do you get? If you add this polarization and this polarization vectorially, you get this, right? So this was the plane of polarization before propagation. Now this is the plane of polarization, and this we can actually call polarization angle, delta theta. Polarization after propagation. So basically delta theta is equal to delta phi by 2. And we can also see this mathematically in the following way, right? So we have, in this case, we have epsilon r hat and epsilon L hat, right? So they are just added up and you get epsilon 1 hat, for example, like this, right? So, so if your electric field was, you know, here was E naught cos omega t epsilon 1 hat. So this would be like, so at t equal to 0, this is E naught and epsilon 1 hat direction. So this is epsilon 1 hat. Right, so now what happens is when they propagate, now your, you know, what happens is this will become epsilon r plus, you know, e to the I delta phi. Right, so you'll have this extra phase and then you have epsilon L hat by 2, right? And you know, you take a real part of this, and what do you get? You get, and you know, real part of this times E naught e to the minus I omega t. Right, if you take the real part of that, what do you get? You get so epsilon 1 plus I epsilon 2 hat e to the minus I omega t. So if you take the real part of this, what do we get? We get, so this is cos omega t minus delta phi plus I sine omega t minus delta phi. And this is just, right, so you have so you know, we can actually just set t equal to 0 without loss of generality. So this will just be cos delta phi. If you take the real part of this would be epsilon 1 hat delta phi. So we can just make t equal to 0. That's not a problem, because all we care about is the phase. And so this the real part will come from epsilon 1 multiplying this and epsilon 2 multiplying that. So I square is minus 1, so minus minus is plus epsilon 2 hat sine delta phi. Actually this is a minus, so this will be minus sine. So minus is plus. Sorry, iota square is minus 1. So this would be actually minus. Similarly, this one will be just epsilon 1 hat, right? Because the real part of the epsilon 1 hat minus, yeah, so you know, so delta phi is 0 for this case, so this is 0. So this is what you get after after rotation. So right, so what do we have? We have by 2. So this is before rotation was this epsilon 1 hat. After rotation it's epsilon 1 hat cos delta phi minus epsilon 2 hat by 2 sine delta phi. So now this is the, this is the polarization after, right? So what is tan theta? So tan theta basically, this is again linearly polarized, right? There is no phase difference between these two. They are, the time variation is the same. There is only amplitude change. So that's why this is linearly polarized. You see, for circularly polarized, there has to be a, pi by 2 phase difference. And you don't have that here. So this is again linearly polarized, except that, this, if it was epsilon 1 hat here, and then this is epsilon 2 here, this angle theta is nothing but, tan theta is nothing but sine delta phi. Just a second.
So I think it will be plus the coefficient of sine delta phi.
Yes, just a sec. I made a mistake actually. The mistake was, in fact, I should really not take the time dependence because that really doesn't matter. The other thing was, so there is, sorry, yeah, there is also 1 plus now. That is what I missed. Right? There is this term, and this is correct, right? There is this and this have to be added. And yes, so tan theta is equal to what? Tan theta is the ratio of, this is sine delta phi divided by 1 plus cos delta phi, right? So this is the right, and this is what? This is equal to twice sine delta phi by 2 cos delta phi by 2 divided by twice cos squared delta phi by 2, right? So basically what it means is that so this is equal to tan delta phi by 2. So what it means is that theta equals delta phi by 2. Okay, the same thing that I was trying to show here graphically, that the change in angle of polarization is half the change in the phase angle is seen here. So I think you see, I have not been very careful about the sign. So sign meaning whether this will rotate in this direction or in that direction. So that one has to be careful about. But what is important in the application of this is that we can actually measure this delta theta. You can measure it. And if you measure it, then, so delta theta basically is equal to, so change in polarization angle is equal to 2 pi e cube by m squared c squared omega squared integral n b parallel ds. So this is the formula that you get out. So if you can measure delta theta, you know the frequency at which you are measuring these, these fundamental constants, so you can learn something about this NB parallel ds from rotation measure, and you already know dn ds from dispersion measure, so you can actually get a sense of magnetic fields along the line of sight from measuring this change in polarization angle. Now I think this, I may have made a sign mistake, but at the end I think this delta theta means that if you're if your So I think theta, delta theta is measured in this sense. So it's measured positive in the. I'm actually not sure whether it's measured in this sense or it is measured in that sense. One can actually figure out from the formulae. But anyway, this is how you relate so this is change in polarization angle, and this delta 5 is the change in the phase difference between the R and L circularly polarized components. Okay, let's see. Right, so again, we are assuming e to the minus I omega t plus I k dot x, right? If you know this, so this is your this is how your electric field goes like, and we can actually write EL. So we can just remove this then vector when we do L and R. This is R, and so you are measuring this at the same time. So let's see. So if your KR, what is it? KR is greater than KL. So at a given place, this term omega is the same, time is the same. So you basically have delta phi is equal to KR minus KL times the distance. So if you have e to the I delta phi, so this delta phi has the correct sign. So this is R minus L. So it will actually have a minus sign, and I have a minus sign here. So what I'm getting is that there will be a so the R wave. So if this is the L wave, at some time the R wave will have a e to the anyway, I don't want to do it right now, but let me actually mention. So you guys, it's simple enough. It's just a matter of plotting these and seeing whether delta theta and delta phi are, how their signs are related. Okay, so let's actually go to the last part of this portion, which is two effects, which I will actually not talk about detail at all. And these are effects of, so this dm and rm are we considered non-relativistic particles, okay, and these are fairly well established. The other effects that you should actually at least know the names of and know a little bit about physically is Cherenkov effect. So in Cherenkov effect, what happens is you have a so Cherenkov effect is you have a relativistic particle which moves with a speed v particle greater than the phase speed of the electromagnetic waves in that medium, right? So the particle moves faster than the speed of light in that medium, not speed of light in vacuum. No particle can exceed speed of light in vacuum, but particles can actually exceed speed of light in a particular medium like water, right? We know that the refractive index of water is something like 1.3. So the speed of light in water is smaller. So what happens when particle moves faster than the phase speed of light in that medium is that is this Cherenkov radiation. So Cherenkov radiation is very important and interesting. So so you recall this kappa factor, which was 1 minus n hat dot beta, which comes about when we were writing this expression for electric field, right? There were these 1 by kappa cube terms, and there was a velocity term. So electric field has a velocity term and an acceleration term. And what we said that the velocity term for the electric field falls off like 1 by r squared, whereas the acceleration field goes off like 1 by r. So this, for radiation, we require acceleration of charges, right? Otherwise this will only give you near field and there is no energy going at large distances. But this actually breaks down. This breaks down if the particle velocity is greater than c by n, where nr is the refractive index of the medium. So what happens in this case is you can have in this case what you can have is because what was kappa? Kappa was 1 minus beta cos theta, right? It becomes 1 minus nr refractive index beta cos theta. So if refractive index is greater than 1, this factor actually can blow up, can become 0, can go to 0. So there were these 1 by kappa cube terms here in this velocity term, and that can make an electric field extremely intense. So what happens is, I'm actually not doing the mathematical derivation at all, but what I am telling you are the physical properties of this Cherenkov radiation. So, it's because of the blowing up of this 1 by kappa cube terms that you can have a particle moving at constant velocity, which is greater than c by nr, can radiate. So the situation is something like this, that you have a particle and it is actually moving, okay, and it is moving at very fast speed, and it's moving in a medium like water. So so this is sort of like so as it moves, these are the light circles. This is where the light is emitted. So this is the location of the particle now. Okay, and it is actually all the radiation due to this constant velocity particle is confined to this cone. This is a cone called Cherenkov cone. So there's nothing coming out here because this so this is 90 degrees and this angle theta. So right, this particle, so this distance is right. So this distance is the speed at which the light travels in this medium. So that's c by nr times t. So this is at t equal to 0, the particle was here, and at time t it's here. So this is the distance traveled by the signal starting from this location. This distance, the height of this cone, is nothing but v particle times t, right? So cos theta is equal to c by nr vp, right? And for cos theta to be for theta to be real, this has to be less than 1, right? Or vp has to be greater than c by nr. So basically particle velocity is greater than the speed of light in the medium. But of course, Vp has to be less than c, right? So this has to be, nothing can travel faster than speed of light in vacuum. So this is the condition for Cherenkov radiation. So what happens is this Cherenkov radiation actually with time it will move along this direction. So along so you have Cherenkov light traveling in this direction, and it actually is very useful by measuring the direction of propagation of this radiation. We can find out the direction and velocity of this particle, right? If this particle is moving very, very fast relative to the speed of light in that medium, this Cherenkov cone can be very narrow. So by measuring the propagation of Cherenkov light in time, we can actually know in what direction and in what and at what velocity is the fast particle moving. So this is, yeah, so this is what the angle between this so this is the angle of the Cherenkov cone. So you know this geometry. This is angle theta. This is the direction of light. This is the direction of the particle. So the angle between the direction of the light, Cherenkov cone, and the direction of motion is given by this. And of course, if cos, if c, if c by nr is greater than Vp, of course, you don't have Cherenkov radiation. In that case, your radiation will, even though the particle is moving like this, your radiation moves in all directions. Your particle is slow. That's the usual case. So this is Cherenkov effect. And the last thing is something called Resin effect. This is another effect that happens in high energy particles moving through a medium. It's actually related, this kappa. So this is, first let me tell you what the effect is. Right, so in a plasma, right, you remember epsilon in a plasma was 1 minus omega p squared by omega squared, and n, the refractive index, is square root of epsilon. This is equal to square root of 1 minus omega p squared by omega squared, which is less than 1. So the refractive index, so plasma's refractive index is less than 1, or V phase is greater than C. We already talked about this. Okay, so this will not, there will be no Cherenkov radiation, right? Because that requires the phase velocity to be less than the speed of light, phase velocity to be less than the speed of the particle. So that is not possible here. So what happens in this case? In fact, what happens is the following. So your kappa becomes 1 minus nr beta cos theta, right? And this nr is actually less than 1 in this case, right? So you remember there was a beaming effect, theta becoming of order 1 by gamma as velocity tends to speed of light and along the line of sight. So all your isotropic radiation gets beamed in an angle of order 1 by gamma. That happens because this 1 by kappa cube factor becomes very, very large. But now because of a refractive index which is less than 1, this actually suppresses beaming, right? It's easy to see because now nr has become small. So that effectively makes the speed of your particle smaller than the speed of light. So, so even if beta is 1 or V goes to C, this 1 by kappa cube will not become as big and this beaming will be suppressed. So theta beaming was order 1 by gamma was equal to 1 minus beta squared. In the end, this was the beaming factor. Now this is corrected, becomes 1 minus nr squared beta squared, where nr is the refractive index, and that is what for a plasma. So this is equal to, I'm taking beta of beta equal to 1, so 1 minus 1 minus omega p squared by omega squared. This is my nr squared. So this is equal to omega p by omega. So my theta, which was 1 by gamma previously, becomes this. So if I plot theta, the beaming, as a function of omega p by omega, right? So at high frequencies, the effect of medium vanishes. So at high frequencies, that is at low, so this is like this is like 1 by gamma. At high frequencies, it's 1 by gamma. At low frequencies, it becomes larger and larger. It becomes omega p by omega. So this is, sorry, this is frequency. So this is at low frequencies, it saturates at 1 by gamma. At high frequencies, it becomes larger and larger. So beaming is suppressed. That means theta b is becoming larger, meaning beaming is suppressed. So if theta b is small, so if you have a particle, this is the beaming. Now if this particle is in a medium, in a plasma medium, you will get something like this at some frequency, and at even lower frequency it will become almost isotropic eventually. Okay, so this is called Resin Effect. And if you recall, the particle picture of synchrotron emission had this beaming in a fundamental way, right? And where does this transition happen from particle to medium effect? This happens when omega p by omega is equal to 1 by gamma, or omega is equal to gamma omega p. So suppression of beaming and hence synchrotron emission where omega is less than gamma omega p. So at very low frequencies, the synchrotron spectrum will cut off because of this Resin effect, which suppresses beaming, and that fundamentally is because of this kappa. Both Resin effect and Cherenkov effect are fundamentally because of this behavior of kappa. So right, and the other thing we note is that for omega less than omega p, EM wave is reflected. Right, this is when the wave frequency becomes smaller than the plasma frequency, there is reflection, but Resin effect is important at much higher frequencies. So what you can actually have is you consider a synchrotron emitting magnetized plasma, right? At very low frequencies, these synchrotron waves will get reflected, but at higher frequencies than that, there will be suppression of beaming. So there will be no reflection, but there will be no synchrotron. There will be synchrotron suppression. So anyway, these effects are important to know. I haven't covered them in great detail, but this physical picture is, one can actually appreciate. So when one encounters it in real life, they are not out of place. Okay, so are there still? Okay, good. So so I will actually end the class. So the next two classes, I think I'll only need two classes. We will change gears again and we will do line formation and line profile and Doppler broadening and things like that. Any final question? If not, then